Thanks for the session itself. My name is Meng from Peking University, China. I will present our recent work, AutoMAP. Diagnose your microservice-based web applications automatically. This study focuses on the anomaly diagnosis problem in microservice-based web applications. As we know, in microservice architecture, each service runs independently and communicates with others by web API. Web applications based on microservices have the benefits of easy abstraction, modularity, reusability, and independent scale. However, they also introduced new challenges for anomaly diagnosis, such as this. First, dynamic application structure means the behavior of application changes over time due to effects like load differences, so static threshold methods don't work anymore. Second challenge is indirect anomaly propagation, such as that services on the same host or container affect each other. This propagation is not included in the core graph, such that methods based on accurate core graph cannot deal with it properly. In this example, the read service is in the same service of the other two services. It is very likely that when read services consumed too much host resources like CPU or memory, the other two services will also experience performance degradation. Third challenge is the existence of multiple types of metric, which makes it difficult to choose the best one for anomaly diagnosis, because certain anomaly only reflects in certain metric. In this study, we use IBM Cloud as our real-world testbed. It's a platform as a service cloud platform. It provides virtual machine, container, and over 200 categories of public microservices, including big data, IBM Watson, data analytics, IoT, security, and extra to help us build, run, deploy, and manage applications on the cloud. The problem scenario of this study is quite general for cloud environments. Suppose an anomaly is observed in a front-end service of web applications. The goal of this study is to identify a set of services that cause the anomaly based on multiple kinds of collected metrics. Okay, next we show our motivation of using multiple metric, which is a core idea in our method. During manual diagnosis, we noticed that experts tend to choose certain kinds of metric to troubleshooting according to the feature of service, such as UI-related services are usually investigated using latency, right? While computation-intensive services such as Hadoop or Spark calculations are suitable to diagnosis using throughput or CPU metrics. This figure shows the metrics we considered in our testbed system. The final problem is, for automated diagnosis, we must design an algorithm to intelligently choose and combine the appropriate metrics for certain anomalies, rather than manual ways. So this is our solution to the problem, AutoMAP, also Automated Microservice-based Web Application Patrol. AutoMAP consists of 6 iterative phases shown in this figure. In the following slides, we will show each phase in detail. The first phase is choosing an appropriate interval for service monitoring. The reason for this phase is that we think it is necessary neither too small nor too large. Small intervals will add plenty redundant fluctuations, while large intervals will possibly lose some details. To consider all services, we use frequency weighted average of request interval as shown in this equation. The next step is constructing a data structure called behavioral graph using these metrics. behavioral graph is defined as a weighted partially directed graph to describe the impact relationship between services with respect to each metric. For example, the edge console to dashboard indicates the change of console will cause the change of dashboard for these metrics with non-zero weight. In other words, the console impact dashboard when considering metric latency and metric availability. To do this, we designed an iterative algorithm. It includes 4 steps. For each type of metric, we start step 1 from a complete, undirected, and fully weighted graph. In step 2, we test conditional independence of any 2 pairs of services for each type of metric. In step 3, we remove unconnected edges and normalize weight of each metric for each edge. Finally, we arrange all weight structures and other edges to get a completely partially directed acyclic graph. The details of our algorithms is given in the paper. As limited time, we will show an example of behavioral graph construction. We showed construction details of a demo behavioral graph using latency for 4 microservices. Here we have 4 services. In order to obtain the behavioral graph between them, we perform the conditional independence test between them. First, we set level equals 0 in G1 and test all service pairs for their conditional independence. In this process, we find dashboard is independent with events and dashboard is independent with AI. Therefore, the edge dashboard to events and the edge dashboard to AI are removed from G1. In G2, we test the independence and find event is independent with AI given dashboard. Therefore, we remove the event to AI edge. Similarly, in G3, we find console is conditionally independent with AI given dashboard and event, and therefore we remove the edge console to AI. The algorithm stops because we don't have enough services to add to the conditional set, so we obtain the skeleton in G4. In the last, we arrange the weight structures and remaining edges by repeatedly rechecking. So we obtain the behavioral graph indicating event is causing console and console is causing dashboard. It's also worth mentioning that the edge weight is metric specific. As we previously said, IBM Cloud System has over 200 categories of microservices. Without any prior knowledge, it's a challenging task to classify various services according to their characteristics. Thus, we aggregate historical weight of behavioral graph of each service by defining an addition operation over graph, given as these equations. The figure below shows an example profile. After calculation, dashboard service gets its highest weight for metric latency, which means it can be best described with latency metric. Thus, we can make a summary of typical categories of service profile showed in this table. Every service has its own best dominant metric. The category are denoted as R representational, C computing, N networking, S storage, and E environmental. Later, we will use this profile to compare similarity between anomaly behavioral graphs. Beyond service profile, we are interested in profiling an anomaly in behavioral graph, considering the fact that service profile only describes correlations in normal status. To remove the redundant normal correlations from the behavioral graph, we designed the subtraction operation showed here. Then we can subtract from the abnormal behavior graph, generating the below example. After removing normal behaviors, we are able to focus on the anomaly behavior itself, like the red arrows showed in the right figure. This graph is constructed using previous steps. We can see that root cause services number 31, number 28, and number 30 are connected. However, if we follow the edge directions, we can only get to the services indicated by green arrows, which is not the root causes. Thus, we designed a heuristic random walk algorithms including forward, self-ward, and backward transitions to help locate the root causes. 3 transitions are defined with this probability quotients. Forward transition. Assume that the random visitors are visiting a node. It has a chance to walk to the next node if they are connected. And self-ward transition. That means the visitors are encouraged to stay longer on the current visiting service if none of its preceding and subsequent services are of high correlation score. A third is backward transition. When the visitor is visiting a service with low correlation score, it won't have any chance to escape this route if all its subsequent services are wrong answers. So we designed a backward transition to help it go back and find more possible routes. These transitions make our random walk more heuristic. If the algorithm only considers forward transitions, it may limit the investigation of a large part of other services shown in the left. But when we introduced self-ward and backward transitions, the random walk can be more dynamic, as the right example shows. Here, red arrows indicate possible walk directions. We find that more candidates can be investigated using our method. In the last, we present how to learn metric weight. This figure demonstrates the overall process of metric weight learning in our self-optimizing module. The motivation of combining multiple metrics is from the way of manual troubleshooting by experienced engineers, that is, if the confirmed root cause in historical incidents show high correlation with the front-end service in terms of certain metric, in similar situations, the candidate root cause services should also have high correlation using the same metric. Given current anomaly behavior graph GA, we use profile similarity to select top k similar historical profiles as G1 to Gk. Then service correlations and result precisions are calculated from historical data, denoted as C and G. Finally, these two information are averaged together as the updated metric weight W1 to Wm. The updated metric weight will be used for behavior graph construction as well as root cause detection in the following stages. As we just introduced, we proposed a similarity function to enable the search of similar anomaly profiles. In order to measure the similarity between anomaly profiles in terms of their anomaly pattern, we consider profiles topology, service profile, and edges at the same time. The 4 steps are shown in this slide. For instance, if G1 is a correlation sequence R to C to S to E, and G2 is a sequence C to C to S to N, their sharing anomaly profile is denoted as G, C to S. Thus, the number of shared services are 2. So, vertex overlap is calculated using as this. For edge overlap, we used the Euclidean distance between the shared edge weight in different anomaly graph. In the last, we showed our evaluation result. The first experiment showed the precision of algorithms for the top K result. We compared the result precision using latency and throughput for single metric methods, TBAC, monitor rank, and cloud ranger. And we chose 2 kinds of multi-metric algorithms, that is, mathematic and MS rank. Their results are calculated after 10 rounds of diagnosis. Overall, the result shows AutoMAP outperforms other algorithms in terms of accurate precision. It provides a precision of 65.7% in top 1 and 93.5% for top 5. Also, for top 5 accuracy, we find monitor rank have an 89.7% precision, which is the rounding up approach. Compared to statistical approaches, mathematic random walk-based methods can discover the root cause more precisely. Besides, compared with the MS rank algorithm, the introduction of anomaly profile in AutoMAP can effectively improve the result accuracy, especially for top 1 and top 3 results. In order to verify the effectiveness of self-optimization mechanism, we examine AutoMAP on multiple rounds of testing and compare their results with the mathematics. This is the result. The precision of AutoMAP increased significantly with the increase of diagnosis round. For example, it increases from 59.7 to 93.9 for top 5 accuracy. AutoMAP shows obvious advantage over mathematics, as mathematics doesn't support self-optimization, so it is unstable in the rapid changing system architecture. We also find that deviation of results decreases with multiple rounds of experiments. In other words, the optimization tends to be stable. Next, we discuss how AutoMAP can be augmented with domain knowledge to improve its accuracy. We proposed 5 enhancement methods using different domain knowledge in AutoMAP, and we observed the result. We find that algorithms enhanced with domain knowledge have different impact on the original AutoMAP. For instance, when length equals 200, domain knowledge can better help improve the algorithm precision, such as API, linked, and direction. However, when length equals 1440, Although the enhanced algorithm can still improve the precision, it is clear that the derived behavior graph is sufficient to be used for heuristic diagnosis. That clearly says the role of domain knowledge gets weaker when more sampling data are available. The next experiment analyzed the running time of AutoMAP onto different parameters. To observe the effect of alpha, we increase it from 0.01 to 0.5 and find the overall execution time increased linearly. However, when alpha equals 0.5, it still takes less than 4 minutes to process the complete dataset. We also developed additional experiment to analyze the effect of alpha and rho on precision. When we increased alpha from 0.01 to 0.5 and compare precision under different lengths, we find that when the dataset is sparser, for instance when length equals 200, higher alpha makes the result more precise. This is because AutoMAP does not have enough metrics to characterize the correlations. When we set alpha lower, the number of edges in the behavior graph may become too few to ensure the accessibility of visitor, leading to low precision. Meanwhile, when we use more metric, records to run AutoMAP, the impact of using different alpha is not obvious. Lastly, to evaluate the impact of the backward transition parameter rho, we set up two experiments as shown in the right figure, and compare the precision using different rho. As the result showed, when rho is smaller, a higher alpha is needed to ensure that the random walk algorithm has more paths to traverse. Okay, let's make a conclusion. In this paper, we present AutoMAP, a system that enables automated anomaly diagnosis for microservice-based web applications. To be more precise, we propose the concept of anomaly behavior graph, and we also defined addition and subtraction operations on behavior graph to use them for the generation of service profile and anomaly profile. The second is we define the similarity function on anomaly profile, which enable us to perform the automated metric weight learning, which helps a lot for our precision. Finally, we leverage the heuristic random walk algorithm, and which included forward, self-ward, and backward random walk. Our experiments conducted in both IBM cloud and simulated environments showed that AutoMAP outperforms other methods in precision. Our future work will be focused on the application of AutoMAP to other complex systems involving multiple metrics, such as social and biological networks. That's all for the presentation. Thank you for your attention. There is one more thing. Our lab is hiring faculties and postdocs. If you are interested, please contact our lab director, Professor Wang. Here is his email address. Thank you again.